Now we are in the third section of the book is the mass transport. But before start the mass transport, let's go ahead and check and review the chapter 1 in the momentum transport by molecular moments, another molecular momentum transport. In chapter 1 we start by the definition of the viscosity, and we talk about Newton's laws of viscosity as a molecular transport of the momentum. Later on this chapter, uh, we just go define the uh, convective momentum transport. We said the momentum can be transported by the molecular movement, also can be transported by the bulk movements. That's why we have to define another term, convective momentum transport. And finally, we define in the end of the chapter 1 the combined momentum flux, which is the sum of the molecular momentum flux and the convective momentum flux defined by this term. And in here the first term is just give the forces is acting on the body of the volume, and second term is this is also a molecular transport of the momentum. Second term is the convective transport of the momentum. So we divided this term is two term. The first one is the momentum transport because of the pressure effects, and also the second one is the viscous forces, and again convective flux, so on. This table is give you the summary of all these terms. This is the definition of the convective momentum flux tensor, and this is the viscous momentum flux tensor, and this is the molecular momentum flux tensor, and this is the combined molecular transport. And as we said in the starting point of this book, actually transport phenomena is included momentum, energy, and mass transport and simultaneously together in these books, because it says they contain analogy between each other. Why? Because all the laws define the transport is similar each other, and all the mathematical derivation similar, and all the solution, all this mathematical um, equation is similar each other. So that's why in here we just like in chapter 1, and when we go to the energy part, chapter 9 is give this similar manner like chapter 1 is defined first energy transport by the molecular movements. We call this define the conductivity, and we define here the molecular energy transports, and in very similar manner like in chapter 1 like momentum transport, so on. Okay, then we just end up here the conductivity in the tree space. Later in this chapter in the energy section, we just again define the convective energy transport, similar momentum. In here in section 9.7 is defined the convective uh, energy transport as like here this term, because of the fluids uh, just carry out some energy with it, like kinetic energy and the internal energy. So also this fluid has also some velocity, and this combination of these things give just us the how the fluid transport the energy by the velocity convective term. So also in section 9.8, we define just the work concept in by the molecular motion. Um, Finally, in here, we define the combined energy flux vector by E, and E contains three terms. The first term, convective transport, and second one, as the work term, and the third one is the conductivity, conduction term, energy transport by conduction, so on. And this table gives again the summary of all these terms and so on. Now we are in here, the section of the mass transport, and in here we start with the chapter 17. Chapter 17 is going to be very similar manner like chapter 1 and chapter 9. It's going to start by the definition of the mass transport by molecular movement, molecular mass transport, and it's going to just be defined the definition of diffusivity and the mechanism of the mass transport, so on. Okay, as you said before, and starting by Newton's laws of viscosity and Freud's laws of conduction, in here, we will define the fixed laws of diffusion. This is the describe the movement of the chemical species A through the binary mixture of the AB. Think about, you have some mixture. It contains two different species. We call them A and B. Inside of this control volume, how the one species, for example A, um, moves through the other species B. We call this movement of the chemical species A through the binary mixture A and B because of the concentration gradients A. Because in here the species A or B, they move from one point to another point because of the concentration gradient, so on. Okay, now in section 17.1, we say is fixed laws of binary diffusion. Binary means you have some kind of mixture and it contains two different species. So molecular mass transfer. Okay, start again, similar manner and similar definition. Think about a system. You have some slab, thickness of your slab is Y, and this slab, let's call this kind of any species, let's call it silica plate, and we call this has contains the area of A and thickness of Y. Is think about this horizontal surface from here, like here, as we defined before. Let's me just draw some 3D picture. We have some horizontal slab. We should consider like this. Think about like this. This thickness is Y, and this is the area is the A. At initially, when the time is here t less than 0, there is the air around this slab, but the air is not soluble inside of this solid, so we don't see any concentration of the air inside of our slab. But when the time is set up as a 0, as an initial starting point of the process, initially when the time is equal to 0, we just replace the air below here by the gas of the helium. So gas of the helium, but this time the helium is different than the air, so helium is uh, soluble inside of the silica in an important level. So let's think about in the time is equal to 0, the concentration of, or we call this mass fraction of, or concentration of the A, we call this the helium, we call the B as a silica, this slab. In here VA 0 initially, but when the time is moved in the small times, we will see the silica just move through in the positive y direction, moves up, and so we see some concentrations through our slab in the small time t. So initially for the small t's, concentration of the helium inside of through the silica depend on the y and t, but after large times we will obtain the gradient concentration distribution of the helium inside of the silica in this form, and this form is independent of the time for the large t, so just dependent on the y in the positive y direction. So This is very similar as we remember from the momentum and the energy. Momentum was transported through the positive y direction, and it's similar. The energy was transported in the positive y direction. Similar in here, the species A, the helium was is transported through the positive y direction. So we call this process the diffusion of the A, the gas of helium inside of the species of the silica and slab. We call this also mass diffusion or concentration diffusion or ordinary diffusion. So it has different names. So then um, in similarly in the chapter 1 and chapter 9 we can define this mass flow of the a per area by the right side equation. Is the rho is here the density, and dAb is the diffusivity of the A inside of B, and VA0 we know the at the time is equal to 0, as it is the concentration of the or the helium and below the slab, and so this the Y is the thickness of the R slab. So from here we call this the mass flow rate of the helium per unit area, or mass flux is proportional to the mass fraction difference divided by the plate thickness, as we see in the right side. Here rho is the density of the silica helium system. Think about here when your helium is inserted or just move inside of your slab, the system is gonna be have A plus B. Then this system has some density is included the silica and the our helium gas. So this is just represent the density of our system, our mixture. So in here, the AB is the diffusivity of the silica helium system. Finally, we can write the differential element for the slab, and we obtain JAY is in here. That's mean molecular transportation A through the positive y direction is defined by minus rho dAb, dWA, and dy. That's mean the concentration gradients of the helium gas is just created some and transportation of the helium from one point to another point, and this is also proportional by the diffusivity of the A inside of B and the density of the mixture. So in here um, we just replace the WAY divided by A by this term. We just define this term molecular molecular in here we just define this term molecular mass flux of the helium in the positive y direction. So okay, just we define this transport molecular mechanism. So we call this mechanism the fixed first law of diffusion. Just define in here the y Vy is just the mixture velocity. Mixture velocity. Then we can define the binary mixture. For the binary mixtures, mean A plus B. And let's say we have some mixtures. It contains two different species. We call this binary mixtures. We can then any inside of any control volume, we can define the velocity of this binary mixture by this formula. Is the WA is the mass fraction of the species A, and VAY is the velocity of the species A. It's not the molecular velocity, it's average velocity of the species A, and plus WB is the mass fraction of the B, and multiply by the velocity of the species B, average species velocity is give the velocity average velocity of the mixture. So in here we know from undergrad courses VA is gonna be equal to 1. So okay, in here the V is the average in which the species velocity is VA and VB. Okay, we define like here. Okay, this kind of velocity is referred as the mass average velocity. In here, we just define this as a mass average velocity. We calculate the mass average velocity of the mixture from the individual species average velocities multiplied by their mass fraction. So then the mass flux in y positive y direction of the mass flux of the species A then defined by this formula. So this is going to be, you see, the relation is going to be equal that one is just multiplied by the rho. Rho is the mixture density. Wa is the species A mass fraction, and we call here concentration or differences, or we define species A average velocity minus mixture average velocity center mass. So you see, in here we have just system is contains two species A B. The system have some, let's say, some the velocity average velocity. Also the species A has some average velocity, let's say we define here VIV. This difference between these uh, two average velocities creates some transport of the species A inside of our system. Is similar valid for the species B also. So okay, let's continue our discussion. In here we can write actually uh, we can write same definition for species B. Y is going to be equal rho WA and V by minus Vy. So let's say we have some center velocity of the mixture. We call this average velocity of the mixture. Then let's say we have some average velocity of the species A and average velocity of the species B. Because of the concentration difference, the species A is going to move from this direction, and species B is gonna go move this from this direction. These are going to be the reverse, and total, not total, individual species mass transport rates is gonna be same number but in reverse each other. So this is going to be, let's say, if this is going to be plus, then this is going to be minus. Let's say this species A mass transport rate, let's say, is going to be plus x, then species B mass transport then is going to be minus x. So then we define this JAY and then JAB. It should be this 0 because this is going to be plus x and this is going to be minus x. Then these are going to cancel each other, and we obtain the in the binary system species mass transport summation is going to be give the result as a 0. Okay, this is the rules comes from the definitions of the in the binary divisions. So okay, uh, in here so far we define our species mm, JAY, for example, in just one direction, in the positive y direction. But let's think about, we have some in system in control volume. Let's say in the control volume, if we are in the tree space, let's say in the rectangular coordinates, we will have x, y, z, or in the cylindrical coordinates, we will have r, uh, theta, and um, uh, actually z, and so in spherical coordinates, and then we can generalize the fixed laws in interior space by this formula. That's mean fixed laws of the species A mass transport inside of the control volume through the interior space by this rho multiplied by dAB is diffusivity A through the B and del WA. This means give the we if you remember del is going to be WA in the X, WA Y, WA Z. So species A concentrations gradient through the in direction X, concentration gradient direction Y, concentration gradient direction Z is gonna give us the total mass transport species A through the any control system, control volume in the tree space. So, okay, let's just move another. So, in similar relation, we can write similar things for the uh, actually for the concentration B. In just we define here the in here we just give the species A mass transport by diffusion by this form. We can write the same thing, similar things for the species B. For the species B, JB is defined as minus rho dBA. This time you see diffusivity BA. That's mean B is diffusion is happening B through the A. And concentration gradients of the B in tree space. In here, actually, dBA and dAB is gonna be equal each other for the pair A and B. And this diffusivity, that's why for the binary systems we can define dAB, dBA is gonna be just one thing, one diffusivity. This diffusivity actually is dependent on the pressure and temperature and the composition actually. So just when we continue our discussion, if you remember before, in the momentum part and the energy part, we just define thermal diffusivity here is gonna just alpha is K over rho Cp. K here is conductivity and rho is density and Cp is the constant pressure heat capacity. The momentum diffusivity is kinematic viscosity is we define just as viscosity divided by the rho. All here is here the dimension of the length square time. Let's say like this, all same dimension. Also mass diffusivity here, DAB or DBA or D, has the same dimension, the length square divided by the T. So there are some relation between these three concepts. Let's say the Prandtl numbers defined is as a momentum diffusivity divided by the thermal diffusivity. Also, Schmidt numbers uh, defined as the momentum diffusivity divided by the mass diffusivity, and Lewis numbers defined as the in here thermal diffusivity divided by the mass diffusivity. So these dimensionless groups of the fluid properties play is important role is dimensionless equation of the system. So if you write your system, let's say you have some reactor, in let's say you derive some the momentum energy and mass conservation equation for your reactor, so you can write all this equation by these dimensions forms and see the effect of the important concepts by defining this Prandtl and Schmidt and Lewis numbers. So okay, now if you just continue in here, and the rest of these chapters continue just define some experimental diffusivities, some the gas pairs, let's say A, B, let's say in here some example. Diffusivity of the between carbon dioxide and nitrogen oxide is given in temperature of this by this form actually, and you can find another binary mixtures here, and later just give some diffusivities or experimental diffusivities in the liquid states from binary mixtures. In here, experimental diffusivity in solid states, let's say helium inside of the, let's say these solids and slab, let's say other things in, and diffusivity is given by this experimental results, so on. And in literature, you can go and find binary diffusivities of the many species, many mixtures. So in here in the section 17.2 it gives some temperature and pressure dependence of the diffusivities. As we said before, diffusivity is dependent on the temperature, pressure, and the compositions. And these theories give some calculation of the diffusivities and how they depend on pressure and the temperature. As we continue in here in chapter 17, is give some examples, and you can go and read and obtain more detailed knowledge and insight of all these theories. And section 17.3 is give some theory of the diffusion in the gas at low density. Uh, you can find in some theories and calculation of the diffusivities from the theory point of view. So again, similar in the binary liquids, some theories, and just chapters continue. I don't just want to go on in detail about this section, and even again suspensions. I just want to go more as polymers again. Okay, we just stop here, and section 17.7 talk about again the mass and molar transport by convection. First, it defined what is the mass and molar concentration. We know what is the mass concentration of the species. In here, we call alpha as any species. As is the mass of the species alpha per unit volume. We call this density. Also, we defined molar concentrations, and is um, relationship between the mass concentration and the molar concentration is given by this formula. This m alpha is here the molecular weight of the species alpha. So in addition, the mass fraction, as we defined before, W alpha is any species. We defined the density of the species alpha divided by the density of the mixtures. We can define in here mole fraction as x alpha is concentration, molar concentration of the alpha divided by the mixture molar concentrations. As we know, the mixture concentrations can be calculated summation of the individual species mass concentration. Similar manner, the mixture molar concentration can be calculated summation of the molar concentration of the individual species, so on. Another concept here important the mass average and the molar average velocities. And let's think about the species alpha. They move by the velocity of V alpha. V alpha mean here velocity of the species alpha, not the individual molecular species, individual molecule of the species, but rather the average all of the velocity of the molecules of the species alpha within the small volume. Think about any small control volume inside of your system. So this system, let's say, is contain the species alpha, and all the individual molecules are inside of system. But we talk about in here as a V alpha is the average velocity of this species alpha. Then by taking this definition, we can define the mass average velocity. What is the mass average velocity? Let's say we have some system. The system contains an species more than one. Then the mass average velocity of this system, defined by V, is by this formula is summation of the individual species mass concentration multiplied by the individual species mass average velocities divided by the total mixture mass concentration or density. You can write this in here. This is going to be equal to that one. Also, we can write that one by this form. That means the summation of the individual species average velocity is multiplied by the mass fraction, and summation of this all the species give us the mixture system average velocity. So on. Okay, okay. So this table is important. It's defined like mass concentration of the species alpha and mass density of the solutions contain more than one species, and mass fraction of the species alpha inside of your system defined by this. Also, we define the molar concentration of the species alpha, also molar density of the solution, and the mole fraction of the species alpha defined by this. If we define m is the for the mixture is the this m here is the molar mean molecular weight of the solution or the mixtures is divided by the its mass concentration divided by its molar concentrations. So any species alpha molar concentration is given by its mass concentration divided by its molecular weight. Summation of the molar fraction is has to be give them 1. Also, individual species alphas mole fractions multiplied by their molecular weight is give them that m is the molar mean um, molecular weight of the solution or the mixture, and we can calculate the species alpha molar fraction by this formula. Again, at the right side is similar manner. It's defined individual species mass concentrations. Summation of the mass fraction has to be equal to 1, and this give this relation and also this relation. So differential relations and gradients any of the species mass fraction molar fractions given by this right side formula or mass fraction this formula. But if your system is if it contains it's binary system, that means just only contain two species, then we can just simplify this equation by this form. So this gives us the species A gradients, molar fraction gradients inside of the binary system by this form, and also mass fraction or mass concentration differences or gradients given by this form. Okay, in here, as we note, is this term is rho multiplied by V. Rho here the mixture mass concentrations. V is the mixture mass average velocity, as the mass passes through the unit cross section plus perpendicular the velocity of the V. That's mean, let's say we have some any plane here, so the fluid is flowing here perpendicular. That's mean the angle between this surface and this vector or tensor is just 90 degrees perpendicular. So I give the rho multiplied by V is give the mass pass through per area in here in this system uh, plus perpendicular the velocity. So from here we can define the local molar average velocity as we defined before mass average velocity as V, but in here V star is given as the molar average velocity is defined similar manner. Molar concentration of the individual species and mass average velocity individual species inside of your system. We can obtain just from here this formula, or this equal to C total molar concentration of the mixture, and just we can write also in this form. This is very similar in above we define how we define the mass average velocity. So in here actually in here uh, similar like CV star is gonna be local rate of mass moles in, like, let's think about before any plane. So the, the species flowing is perpendicular to this plane. So this defines CV star is give the moles is flowing through the unit cross sections is perpendicular to molar velocity of the V star. So we just obtain rho V mass passed through this cross section area. C multiplied by V star is molar moles flux through this areas. These are different than each other. So okay, just continue our discussion here. Just okay. Uh, so V alpha is the velocity of the species alpha with respect to fixed coordinates in the mixture in the control volume. We has defined the mass average velocity of the system different than that one. It's just not that is just alpha is any species, and V star is the molar average velocity. This is mass, this is the molar. So then V alpha minus V here the average velocity of the total system, and V alpha is the average velocity of the species alpha. Is give the diffusion velocity of the species alpha with respect to mass average velocity of V. So again, V alpha minus V star is give the diffusion velocity of the species alpha with respect to molar average velocity of V star. So addition relations, V minus V stars give that one result. V star minus V is give that result. Okay, just go move next part. In here we just go the chapter section molecular mass and molar fluxes. Before we define, if you remember, J alpha was rho alpha multiplied by V alpha minus V, just was giving the mass flux per unit area. Then we can define from here JA star here, CA multiplied by VA minus V star. In here, just replace the alpha by the A and the species. So here we just define here the molecular molar flux of the species alpha or A here, most alpha flow through the unit per area time. So okay, now we have the relations, the mass units, mass diffusivity, mass or flux defined Ja is given by this form. These are equal each other. Molar units or in the system, we can just define the molar flux by this form so far. So the difference between Va minus V and Va minus V star is sometimes referred to diffusion velocities. Diffusion velocities. Just results the species transport from one point to another point is just like a concentration gradients. Okay, in the next parts, convective mass or molar flux, as we define as before, convective transport of the mass was defined as just the velocity vector is perpendicular to the surface is given like, let's say this is the x direction, Vx multiplied by rho or the species alpha. Another, if we reverse this, like say like this, it's flowing from here, let's say this is the z direction, then the mass flux from here Vz rho alpha. Again, let's say another term like here, let's say it's flowing from here, this is the y direction, z direction, y direction. Now we can define the max flux from perpendicular to the surface as Vy and rho alpha. Again, for the molar flux, we can define here Vx multiplied by C alpha Vy multiplied by C alpha, V Z multiplied by C alpha again. So we call this actually convective mass or molar fluxes. So as we define here, as we see, is give this summation of these three terms, summation of that one is the first one, x in the x direction, y direction, z direction. We obtain this v, the velocity, average velocity of the species in the three space coordinate in the control volume. If you multiply by the mass density of the species alpha, is we obtain convective mass flux vector. It is the units of the kilogram per meter square multiplied by second. Similar manner, we can write here uh, in the x direction, y direction, z directions. We star. Okay, we made mistake. It should be here in c alpha v star, not the v. We forgot to write the v star here. Anyway, then we can define this term convective molar flux vector is mole divided meter square multiplied by seconds. Okay, now we come just the section 17.8 summary of the mass and the molar flux. Okay, as we defined before, the combined momentum flux like this term and the combined energy flux by this E. Now we can define the combined mass flux are similar to combined molar flux. Combined mass flux uh, for a system, we can define small n alpha, j alpha plus rho alpha v. In here, v is the mass average velocity, don't forget. Combined molar flux is defined big N alpha. J alpha is the molar diffusivity or multiplied by the convective molar transport of the species respect the average molar velocity. So these are two important uh, results we obtained from so far here. In here, the fluxes J alpha star mass flux with respect to molar average velocity, and J alpha here molar flux with respect to mass average velocity. Okay, now again in the next part we can write these two relation also. Okay, everything's in this chapter about the molecular transport of the mass on the convective transport mass. Just summarize here. Let's say the velocity of the species alpha is defined by this v alpha is centimeter per second, and with respect to mass average velocity, this is the species average velocity, is respect to mass average velocity, center velocity is given by this, and with respect to molar average velocity is v star. We define all these things above. Now about this system, what is the mass flux of the for the species alpha is gram per centimeter square per second, defined by n alpha is rho alpha v alpha. Don't forget, this is not the system average velocity. This is the species individual species average velocity. This give the mass flux of the species. If we go above, we define the mass average velocity is like combination of the diffusive flux and the convective flux. But this is the you remember this, the v is not the same as here, because in here you just have species alpha velocity. So now with respect to mass average velocity, which we can just write that one for the J alpha diffusivity, which one, and with respect to molar average velocity, we can write the molar diffusion term here, and molar flux of the species and alpha we can write C alpha V alpha. In here again, V alpha is this individual species average velocity and C is the molar density. And we can write respect the average velocity here. J alpha is here And here the diffusion term, and J alpha star is again the mass diffusion. J alpha star here the molar diffusion, and some of the mass fluxes. Let's say you have some system. In your system you have more than one species, and this species have some total mass flux defined by this. Summation of this flux is going to give the result of the rho v, but respect the average velocity and summation of the diffusion terms is going to give the zero. This has to be zero as I defined before. But for the with respect to molar average velocity, the molar average molar diffusion not necessarily has to be zero. Uh, we can calculate from this form. So sum of the molar fluxes, we can obtain molar fluxes this time is again molar fluxes in respect to mass average position doesn't have to be zero as we obtain this result. But this time respect to molar average velocity, sum of the molar fluxes has to be zero. So the relationship between the mass and the molar fluxes obtained by this formulas. These are m alpha is the molecular weight of the species alpha and so on. And interrelation among the mass fluxes as we defined above, diffusion term plus the convective term and so on. For the molar fluxes we define like this and so on. So the different forms of the fixed laws, so Ja here the flux, mass flux, and gradients we just del Wa, we can write by this form. Molar flux we can write by this form. Total mass flux we can write by this formula is diffusion term, and this is the convective flux. And Na again here molar flux, total molar flux can be written here, so on. Okay. As a final final concept, we just call this Maxwell-Stefan equation for the multi-component diffusion, the gas at low density. We can utilize this relation. We call this the Maxwell-Stefan relation to calculate the multi-component diffusions in the gas at low density. In here, gradient of the any species alpha is equal to at the right side. It's as written here. So on. This is the end of the chapter 17. Actually, in chapter 17 we define the mass transport by molecular transport and mass transfer by convective transport as similar to chapter 1 and chapter 9. And the next video, next lesson, we are just going to go and touch and just review some concept in chapter 18 and just chapter 19 and just continue our discussion by this order. See you in the next video.